All right, let's just jump right in. We're going to tackle one of those topics that's become a cliche for being impossible to understand. You know the one. We're talking about quantum mechanics. And where do you even start? Well, how about with the legendary Richard Feynman? This quote is famous for a reason. It perfectly captures that feeling of awe and, let's be honest, maybe a little bit of dread that a lot of us feel. It sets the whole thing up as this big, scary, unsolvable puzzle. But then you get this. Physicist Mark P. Silverman has a much more direct response. He calls that whole idea that nobody understands quantum mechanics, well, balderdash. And that's the wild argument we're going to explore, that maybe that famous quote is just plain wrong. Okay, so let's unpack this. This whole reputation quantum mechanics has as some kind of unknowable mystical force. Is it really beyond us, or have we just been looking at it the wrong way the whole time? Silverman makes this brilliant point right off the bat. He says we mistake being familiar with something for actually understanding it. I mean, think about something basic from high school physics like F equals ma. We all just accept it. It feels normal. But do you really know on a deep, fundamental level why that's true? Not really. We're just used to it. And that's the trap. We confuse that feeling of familiarity with genuine understanding. And this analogy he uses is just perfect. Think about a mathematician who works with, say, 10-dimensional geometry. They can absolutely understand the rules. They can do the math, make predictions. They know that world inside and out. But ask them to draw a 10-dimensional cube? Nope, can't be done. Our brains just can't picture it. And that's the entire point. You can understand the rules of something perfectly without ever being able to visualize it. They are two totally different things. So if quantum mechanics isn't just a random collection of spooky mysteries, then what is it? Well, according to Silverman, the entire, magnificent, and yeah, admittedly strange, world of quantum theory is all built on one single core idea. This is really the heart of it all. And here it is, quantum superposition. Now, before you tune out, the most important words on this slide are abstract probability amplitudes. This is so key. We're not talking about a physical particle being literally smeared out like butter on toast. We're talking about a mathematical description of probabilities. An electron isn't really in two places at once. It's in a state where there's a certain chance of finding it here and a certain chance of finding it there. And this idea isn't some minor detail either. It shows up everywhere. You have it in space, which gives you the famous double slit experiment. You have it in time, where a particle's properties can basically flicker back and forth. And you have it internally, like when a particle's spin is both up and down at the very same time. It really is the fundamental rule of the game. Okay, so now that we've got our secret weapon, this core idea of superposition, let's use it to take on the most famous and most misunderstood thought experiment in all of physics. Yep, Schrödinger's cat. We're going to see why, in the real world, cats just can't be ghosts. Now, this is crucial to remember. Schrödinger didn't invent his cat paradox to show off a deep quantum mystery. He did it for the exact opposite reason, to show how completely absurd it was to apply quantum rules to big, everyday things. He himself thought it was a ridiculous example. Silverman has a great term for people misinterpreting this. He calls it quantum flapdoodle. So if a real superposition isn't a blurry, half-dead cat, what does it actually look like? It looks like this, an interference pattern. When a particle's possible paths are in superposition, their probability waves interfere with each other, creating these distinct stripes. This pattern is the physical fingerprint, the hard evidence that tells you superposition is really happening. Which, of course, leads to the big question. If a tiny electron can do this, why can't a baseball? Why don't you leave an interference pattern when you walk through a doorway? What's the dividing line between their quantum world and our everyday world? The answer has a name: decoherence. And what this graph shows is that quantumness, that ability to be in superposition, is just incredibly fragile. The moment a quantum system interacts with anything at all, heat, a collision, you name it, it loses that special state. And the bigger and warmer an object is, the faster this collapse happens. And by fast, I mean unbelievably, mind-bogglingly fast. For something the size of a cat, or even a tiny speck of dust, any potential superposition would collapse in about 10 to the minus 31 seconds. That timescale is so short it's practically meaningless. The superposition never even really gets a chance to exist. But let's just pretend for a second. Let's say decoherence wasn't a problem. Even then, the interference pattern for something like a cat would have waves that are billions of times smaller than a single proton. So it's not just that we can't observe it. For all practical purposes, a pattern that small simply isn't there. So, okay, cats are out, no ghost cats, but that doesn't make superposition any less important. In fact, once you stop trying to apply it to house pets and start looking at where it does apply, you realize this one idea governs an incredible amount of stuff across the entire universe. I mean, look at this. Superposition is the rule for every single elementary particle. It's the engine behind entanglement, that spooky action at a distance. We use it in tiny electronic circuits. It's even thought to be what stops superdense degenerate stars from collapsing. Some physicists even think it could be tied to the very nature of dark matter. This is a truly universal principle. So, you see, by focusing on this one core idea, we can completely shift how we look at quantum mechanics. It stops being this haunted house of weird paradoxes and starts looking like a logical, cohesive theory. This right here really sums up the whole takeaway. The popular view is that quantum mechanics is this jumbled bag of weird things. Schrödinger's cat, wave-particle duality, uncertainty. But Silverman's view, the one we've been exploring, is that it's all one unified theory. All those strange effects are just different consequences of that one central rule, the superposition of probabilities. And so, let's end with this thought. We tend to think of quantum weirdness as the strange exception to our normal, solid, predictable world. But what if we've had it backwards this whole time? If the fundamental rule of the universe is a shimmering sea of probabilities and superpositions, then maybe it's our concrete, one-thing-at-a-time reality that is the real mystery that needs to be explained.